in a high carbon world where more carbon emissions are going into the atmosphere and how that might be affecting the coral reef. Now, it's fantastic to be here at the Kamabi Research Station, give you a quick tour around where we are. It's a building just next to the coast. You can hear the waves behind me, but it's a home from home for scientists from around the world to come and study this amazing environment. So they've got somewhere to stay, but most importantly, they've also got research facilities that will allow them to study samples from the coral reef in greater depth, whether that be in a wet lab with mini aquaria or using other experimental techniques, studying coral babies under a microscope and all that kind of thing. But most importantly, as I said before, all the dive equipment, meaning that scientists can get out on the reef and study this amazing, amazing environment. Now, today's lesson is all about human impact on the reef, and what we're going to do is just a few things. We're going to go through some of the basics of how corals are being affected by higher concentrations of carbon dioxide in the atmosphere. We're then going to do two activities, one of which is called ocean acidification in a cup. The second is dissolving coral in vinegar. We'll come to what those terms mean and how those activities are going to work in just a bit, but all those resources are linked from the lesson page. After that, we'll have a broader discussion driven by your questions, all about human impact on coral and perhaps some of the solutions to create a positive future for the reef. So to start off with, we are looking at carbon dioxide, and we know over hundreds of thousands of years that the levels of carbon dioxide have varied in the atmosphere. But what is happening at the moment is a startling increase in those levels, and that is driven by human activity. At school or through the media, you may have learnt about some of the ways that carbon emissions are getting into the atmosphere. Everything from transport, so the use of fossil fuels such as petrol, or even some transport driven by natural gas. We've also got construction and industry, again using fossil fuels, creation of energy, and also other aspects such as the production of food, and especially high carbon, high intensive farming for things like meat. Those increased levels of carbon dioxide are having two impacts on the ocean. The first of which is ocean warming, and we'll come to something called coral bleaching after we've done the activities. But one of the lesser known impacts of high carbon dioxide levels in the atmosphere is a process known as ocean acidification. Ocean acidification is really just looking at the acidity level of the ocean. And to measure that, we use a scale called the pH scale. And that really just measures the amount of hydrogen ions in a substance. Now, you may have come across the pH scale in science before, but it goes all the way from sort of 14 with sort of things like bleach, all the way down to 0 for highly acidic substances. One of the little bit of confusing things is as the acidity increases, the pH goes down. So when we talk about ocean acidification, we're talking about the scale going down just a little bit. We're not talking about it getting like sort of lemon juice, some of those more acidic substances. So what we're going to do is, I think we're going to get a slide up just to talk you through the process of ocean acidification, and then I will talk you through a little bit of one of the activities and we'll see that process in practice. So essentially what happens is that carbon dioxide from the atmosphere is absorbed into the ocean. Through a chemical reaction, that forms a weak acid known as carbonic acid. And through that process, what we're seeing is the pH of the ocean is decreasing. So what I'm going to do now is talk you through a little bit of that and some of the levels that we are seeing at the moment and some of the levels we might expect in the future. So for this first activity, we're going to need just a few things. We're going to need a glass or container of water. We're going to need something to measure the pH with. I have an electronic pH meter, but you can also use other ways of checking pH, such as litmus strips and also natural pH indicators that you can make from red cabbage. A bit smelly, but we can talk through any of those in just a bit. You'll also need a straw. And what we're going to do is we're going to add carbon dioxide to our mini ocean, and we're going to see how the pH might change with that addition of carbon dioxide from our exhalation, from our out-breath. The ocean waters behind me are going to be probably about, like we can measure them afterwards, about pH sort of 8.1. Since the beginning of the Industrial Revolution, since about 1750, we have seen the average pH of the ocean drop from about 8.2 to about 8.1, becoming more acidic. Now, that decrease of 0.1 of a unit of pH may not sound like a lot, but because of the way the pH scale works, that in fact represents a 30% increase in acidity. Just to put that into context, if you had a 30% increase in acidity in your blood, you'd be in an ambulance straight away to intensive care at a hospital. But let's see whether this idea of adding carbon dioxide to water and that pH changing actually works. So what we're going to do is we've got our glass of water, and it's really, really important if we're measuring change that we measure the level beforehand and then afterwards. So I'm just going to put this glass down, get my pH meter, turn it on, give it a good swizzle, and see where we are. So Ellie, who's behind the camera, I don't know whether we can zoom into that figure. It's probably hard to read on its side, but I've got to keep it in water. 6.81. And it's a little bit below sort of pure water. That could be because I got a knock on my pH meter in the flight over, or perhaps because this comes from a desalination plant and may have even lower levels than we might expect ordinarily in tap water. I wonder what levels you got. So if you're following along live, just to give you a moment to take measurements of your water and note those down. Going to turn that off, and when we're all ready, I'm going to start to add carbon dioxide to this glass of water, and I think we'll go for, Ellie, what do you reckon? 1 minute, 2 minutes? We'll try a minute first. Okay, so everybody ready? If you are doing this in the classroom live or even afterwards, remember not to have your glass too full. I could probably tip a little bit of water out here. And then to blow steadily, not too fast. And of course, if you're doing it in a small group or a pair, remember each to have your own straw as well. Okay, so whenever Ellie is ready with the countdown.
3, 2, 1, go. Halfway.
So what we've been doing over the past minute, and I hope that you've been doing in the classroom too, is we've been adding carbon dioxide to our mini ocean. Now, if the theory of ocean acidification is correct, then what we should expect is that the pH of our mini ocean has gone down. So I'm just going to put my pH meter in here again, switch it on, and see what's happened. So you should be doing the same thing in the classroom, adding whatever indicator that you're using and seeing if there is any fall in the pH of your mini ocean, or in fact rise. But the hypothesis, the prediction that we have, this process of ocean acidification, is that by adding more carbon dioxide, the pH should go down. So I just turn this round. And if I hold that up there, is that okay?
5.07.
5.07. So we can see that by adding that carbon dioxide just over a minute, we have changed the pH of our mini ocean by about 1.7 units, which is quite significant. We don't expect that kind of radical change in ocean pH to be happening in our oceans. Some predictions looking at sort of 7.8 perhaps by the end of this century. But why does all this matter? We're not getting to a lime juice ocean, so why does all this matter? And it really comes down to the type of organisms that we're looking at. And I'm going to come back to the coral. And I've got some examples of coral just in front of me here. I don't know which one to pick. I'll pick this one, this bit of brain coral here. Now, as we've been discussing over the week, coral is a creature related to the jellyfish, related to the sea anemone, a tiny polyp-like creature that grows as a layer and creates this incredible structure underneath it. So as it grows and grows and grows, it grows this structure underneath. Now this structure is calcium carbonate, and the problem with a high CO2 ocean or a low pH ocean, higher acidity, is that this starts to make it more difficult for the coral to create its structure because it affects its ability to form these carbonate ions. or this calcium carbonate. So what we're going to do to see how a coral might react to a more acidic ocean is we're going to use a substance that is very acidic. We're going to use some vinegar, and we'll test the pH of it in just a bit. I'm going to add some coral to it. If you're in the classroom, of course, calcium carbonate also comes in the form of chalk. So instead of using a piece of coral, you can use chalk in the classroom. So I'm just going to take my pH meter out, switch it off, put my water down here, and fill up with some vinegar. Here we are. Put that to one side. I'm just going to see what the pH is here. Pretty low. We're getting down towards a pH of 1, I think, there. I'll just hold that up to make it easier to see. 1.2 there. I'll rinse this off just so we don't destroy the sensor. So super low pH here, and what we're going to do is add some coral into this highly acidified ocean. I'm using blue chalk just to make it easier for you to see. And if I hold that up or put it further towards, does that make it easier? What we can see here, I mean, it's so acidic, the vinegar, compared to any predictions of what the ocean is going to be like. But you can see that reaction between the acidity and with the calcium carbonate. And so what that means is that if corals are finding it difficult to grow, having to put more energy into creating their skeletons, they'll have less energy to fight off predators, to fight off disease, for reproduction and other processes. So just to go over what we've covered so far, we've looked at these higher levels of carbon dioxide in the atmosphere being absorbed into the ocean, changing its pH, and then that change in pH being harmful for organisms like coral that have a calcium carbonate structure or skeleton. And just before we come on to the question and answer section of this live lesson, I want to just touch on one other process that is happening to corals because of higher levels of carbon dioxide in the atmosphere. I'm not going to go into the greenhouse effect and how higher carbon emissions are causing climate change. But that climate change isn't just happening on land, it's also that extra heat is being taken up by the ocean. And this is affecting corals. And I'm just going to lift up the coral again. As I mentioned before, coral is covered in this thin living layer of jellyfish-like creatures, the coral polyp. Like a jellyfish, they're see-through, and so ordinarily you would see this white color for coral underwater. But reef-growing coral have a turbocharge. They have small algae inside their tissue. And this algae supplies between sort of 50 and 90% of their energy, helping to grow the amazing reef structure. Now, if there's a temperature change of just a few degrees, the relationship between the algae and the coral polyp can break down. The algae leave the coral polyp, and instead of the brownish color that you see on a healthy reef, you see that white color of just the calcium carbonate limestone skeleton underneath. Now, this doesn't cause the polyp to die immediately. It has some fat stores, just like us, we could survive on. But its energy intake is decreasing from about half to about a 20th of what it usually is. And over an amount of time, if these high temperatures persist, then the coral polyp can eventually starve to death. Starvation leading to an overgrown and algal slimy reef, and not supporting the multitude of fishes that you would normally see on a healthy part of the coral reef. So there's two ways in which high carbon dioxide levels in the atmosphere can affect the coral reef. We have ocean acidification and we have coral bleaching, driven mostly by higher ocean temperatures. We're now going to come to the Q&A section of the live lesson. And just to go through some of those questions, we've got a feed issue just on the mobile phone, which I use in front of me. So I'm going to ask Ellie, who's behind the camera, to shout some of those questions over. Cool.
Archie, what can we do to stop coral going extinct?
A question through from Archie asking, what can we do to stop coral going extinct? Now, coral is facing many stresses, many impacts on its health. The stress that I've talked about just now is driven by higher concentrations of carbon in the atmosphere. So, Archie, if you're looking to prevent coral extinction, what we really need to do, and what is being discussed at the COP26 summit at the moment, is lowering carbon emissions. So on a personal or school or community level, there are a few things to consider, probably three areas, broad areas to get a start on. The first is what you eat. So considering eating a lower carbon diet, including sort of less meat, going towards a plant-based diet. To start off with, meat-free Mondays, think about that. Think about how you travel. So are there better ways to travel to school that require less carbon? For instance, walking or biking rather than taking fossil fuel-based transport. And then the last one is sort of how we live and the amount of stuff that's being created, all of which has a carbon budget, creates carbon emissions when it's made. So I know that some schools in North America are watching, we're heading towards Thanksgiving and even the run up to the Christmas period. Perhaps we could think about giving each other experiences rather than things, and consider how much we actually need. It's a great question. Thank you very much, Archie.
Can corals adapt to more acidic waters, and can they recover?
So the question is, can corals adapt to more acidic waters, and can coral recover from ocean acidification? It's a really, really great question. In terms of the adaptation to more acidic waters, there's two problems with that. First of all is the rate of change. So at the moment, the reports that I've been reading show that the rate of change in terms of ocean acidification are happening too fast for adaptation to keep up. Having said that, what scientists are studying are those corals that are more resilient, so better able to withstand the changes being brought on by a high carbon world. Now, if they can find traits or things about these more resilient corals and find out how they're being more resilient, there is a chance that this information can be used to support corals and reefs that aren't doing so well. So it's a really, really great question. And just on the acidification piece and even the bleaching piece, yes, coral reefs can recover. And this has happened time over time over time in the past. And I come back to this rate piece. There's been warming ocean events in the past, and these have caused bleaching, but they haven't been that frequent. And it's the frequency of these big events on coral reefs that's posing so much of an issue. If there was a major event, whether it's a storm or warming ocean every 30 years, in those years between, and the conditions are fine, the coral can recover. But if an event that is really harming the reef is coming every 2, 3, 4, 5 years, there is never an opportunity for that reef to recover properly. It's a really great question. Thank you very much for that.
Do we know how much coral is being lost because of acidification?
Do we know how much coral is being lost? Certainly, we're going to come to some of the graphs a bit on some of the lessons next week, especially on Monday and Wednesday. But it really varies from reef to reef. I don't have figures to hand, but we can see on some reefs, studies, in fact, on the Great Barrier Reef, one of the most studied reefs in the world, seeing up to sort of 50% coral loss. I mean, people are talking about, historically, perhaps 80% of coral loss in the Caribbean as a whole. So we do have these ideas of a lot being lost, but where we are here on Curacao, also steps being put in place for restoration and recovery, particularly with the formation of a marine protected area, marine park, on the east point of the island.
A recap again, please, of the main causes of ocean acidification. What are the main ones?
What are the main causes of ocean acidification is the question. So ocean acidification is caused by increased carbon dioxide levels in the atmosphere. Some common ones that you may come across include energy production, so electricity, especially using fossil fuels. There are, of course, renewable forms of energy, solar and wind, but using sort of coal, gas, and oil to create electricity. Transport, using again fossil fuels to drive transport, and then high consumption of carbon in various industries, such as the meat industry and construction industry, such as the creation of concrete. So really thinking about how we can minimize excess carbon dioxide in the world, and we've heard the term net zero. So it is all part of that debate.
Do you think events like COP will help protect the coral reef?
Do we think events like COP will help protect the coral reef? There was an amazing announcement, and I'm just remembering all the countries who signed up to it. Just give me one minute. We have, here we are. So we have, there's a mega marine protected area being created in the Pacific, and that's Panama, Colombia, and Ecuador announced that last week. So certainly at events like COP, there are these ocean announcements, these ocean protection announcements being made, which go towards protecting areas of the ocean. At the same time, of course, there are commitments being made to drive down levels of carbon dioxide in the atmosphere. Emissions is what they're known as. Are these going far enough? I've seen comments in the news today, and I haven't been keeping exact track of the COP negotiations, but it was reported that some scientists were disappointed with the level of commitments being made, and that we need to go further if we want to protect amazing ecosystems like the coral reef.
And then, how is the coral reef here in Curacao different from other reefs like Great Barrier Reef?
Great question. So how is the reef in Curacao different from other reefs such as the Great Barrier Reef? I mean, first of all, there's size, but then also there's sort of less diversity here. We're further away from the center of coral in sort of around Southeast Asia, the Coral Triangle, and as you come further and further from there, you find less diversity. So we'd have probably 70 species of hard coral around Curacao. That would be up to sort of like 5 times that, sort of 350 species of hard coral on the Great Barrier Reef. Also, a lot of the damage has been done to the coral reef in the Caribbean in the 80s. There's a lot of disease, a lot of overfishing affecting the health of the reef in the Caribbean overall. And I think there was a belief on the Great Barrier Reef that it was sort of too large to fail, to use a term like that. It was just too big to be affected by all these changes. What we've seen in recent years, of course, is that's not true, and these mass bleaching events occurring around the Great Barrier Reef. So I'm just sort of listing some, we could spend all day sort of listing differences between the Curacao Reef and the Great Barrier Reef. And I suppose some of the dominant corals you find here aren't really that common, or really aren't found on the Great Barrier Reef. So brain coral and elkhorn, you'd find more of the sort of big boulder corals and staghorn, and sort of branching plate corals and various other corals on the Great Barrier Reef. So it looks quite different.
Should we be hopeful or worried for the future?
The next question is, should we be hopeful or worried? Both. Because if we don't have that worry, and as Rene was saying in previous lessons today, that sort of anger to drive us, then we may not move fast enough. But there are examples of reefs getting better around the world. There are examples around Curacao of the reef improving. And if we do act, we can make a difference. So it's not too late, but now is the time to take action.
Is there a way to make the ocean less acidic? Can you add an alkaline to it?
Yeah. So the question was, is there a way to make the ocean less acidic? The ocean and the planet does that by itself through the weathering of chalk and calcium carbonate into the ocean, such as the White Cliffs of Dover in the UK. And that helps to balance the pH. It's a process called buffering. So that process has been in a natural balance over time. What I think the question is driving at is there an ability to geoengineer or bioengineer? So can we sort of have a sort of technical solution to solving an issue like ocean acidification? And the answer is it's been investigated, but at scale, it really probably isn't realistic. Some of the things that people have been talking about are adding iron filings to the ocean to stimulate the growth of algae that will take up some of that dissolved carbon dioxide. Some people have said, well, there's enough iron in whale poo, so we should just get more whales to poo in parts of across the ocean, and that will help. The scale of those bioengineering, geoengineering solutions simply really aren't up to it, and it's really down to us to reduce our emissions.
Which species are most at risk from ocean acidification specifically?
Which species are most at risk from ocean acidification? It's a really good question. I don't know specifically. I'd have to ask an expert on that. Some of the work I know that's been done on Heron Island on the Great Barrier Reef, just off the coast of Australia, has been looking at that combined warming and acidification. I don't know of a study that's just looked at particular species being most at risk just from ocean acidification. Great question.
And final question, do you think, how do you personally feel, do you think we're going to get there in time?
So I've just been slightly sort of stunned into reflection by the final question, which was like, do I think that we're going to do enough to stop the coral reef from disappearing? I don't know, is the honest answer. Personally, I'm really glad that we're broadcasting you back from Curacao. I'm glad that I've been amongst this community of scientists again. I have to say that I found lockdown tough, and lockdown distanced me from the natural world and perhaps stopped me from being as active as I had been in the past. I hope that in some way through these broadcasts, through AXA Coral Live, we've been able to share some of that passion, share some of that beauty. And really the past week has re-energized me and made me reflect much more on my personal responsibility and then into two other things, which is sharing that and advocating for changes in policy. My particular piece is around ocean education. But there's so many good campaigns to get to out there to really put our natural world further up the stack of priorities when people are making decisions. Because without it, A, we will find it tougher to live on this planet. But secondly, we are diminished. I think, without the beauty of the natural world, without its impact on our souls, for want of a better word, we are less. A long way round of saying, I've realised I need to change faster, and I hope you might feel some of that too. Do we have any more questions, Ellie? Thank you so much, and what a question to end on. I mean, that's really made me reflect. Thank you for that. It's a difficult topic. It's a difficult topic, and throughout today we've been talking about feeling sad, feeling angry, talking about the science, how science helps us understand what we need to do to change. And I hope that if you've been at all affected, whatever the environment, doesn't need to be the coral reef. We're here because it's one of the ecosystems that might disappear first. Please, please, please take time to reflect and look at how you can turn that sadness and anger into positive action. It's not too late. There is hope. And take this weekend to reflect on that and maybe come back after the weekend or during the weekend as a family or a class or a community to consider what you'll do to maintain and restore the wonders of our planet. Thank you so much for being part of this live lesson, looking at the human impact on coral. But for now, it's goodbye from AXA Coral Live, and we look forward to seeing you next week. Goodbye.